for giving me this opportunity to talk at your esteemed institution. It's very interesting to kind of meet so many different people from all over. And this is an interesting concept. I mean, doing Zoom talks all the way through. If people have any need to kind of ask me questions, etc., please go ahead and perk up and just speak up in the middle, and I'll go ahead and slow down and talk about whatever it is that you ask about. So with that, let me go ahead and launch the talk. And so what I'm going to talk about is new capabilities for modeling spherical systems in astrophysics, namely geodesic mesh MHD. And most of this talk is going to be focused on modeling magnetic massive stars in 3 dimensions. And that's kind of what I'm interested in. I would actually point out excellent work that has been done by my student Setu Subramaniam, excellent fellow. If anyone's looking for a brilliant young man, this is the guy. I've also had some very good collaborators to help me along the way, namely Mark Gagne and Asif Uddella on this topic. So let me go ahead and start by laying out the problem. So the problem essentially is this, that many astrophysical systems are very strongly spherical. And so we actually want to do those simulations of spherical astrophysical systems in a format that is actually favorable for spherical geometries. As it turns out, unfortunately, the simulations that we do are actually done in r theta phi coordinates. And here's an example of an r theta phi coordinate in 3 dimensions. And you can actually see that as the zones come closer and closer to the pole, the zones become smaller and smaller. And as a result, you have various difficulties that arise when you try to attack a spherical problem in an r theta phi geometry. In other words, there's a coordinate singularity, which is entirely a removable singularity, and it nevertheless clobbers any simulation. So what it does is it actually destroys your time step. So it makes your time step very small, and it also destroys the accuracy of your simulation. And to make matters worse, there's actually a fictive heating of gas that flows around the pole that happens, and that is kind of the more pernicious thing. So it basically makes it impossible to kind of trust the thermodynamics of the material that is flowing around the poles. And furthermore, magnetohydrodynamics requires a divergence-free representation of the magnetic fields, and we cannot achieve divergence-free representation of the magnetic fields at the poles or anywhere else as a result thereof if we use an r theta phi geometry. So what we want to do is move over from the panel on the left to the panel on the right, which is more oriented towards uniformly covering the sphere with these small triangulations to make sure that we can actually avoid any coordinate singularity, but never having a coordinate singularity to begin with. And if we can do that, and I will show you that it has been done, then we can actually go ahead and do many interesting astrophysical problems, namely problems involving accretion disks and magnetorotational instabilities, but this time done globally. Namely, many of these accretion disks are flaring structures. They're ideally suited for geodesic meshes. Likewise, propagation of jets in galaxies. Likewise, problems associated with star and planet formation. Likewise, we would actually go ahead and love to do problems associated with the heliosphere. As you know, India is kind of investing big time in solar weather. So they basically want to know how actions happening on the surface of the sun will actually affect us on Earth. So they're interested in solar weather. We're actually interested in magnetospheres, not just of our sun, but also interested in magnetospheres of stars and planets. and that's one of the topics that I'll be talking about. Again, the sun is a convective system. The AGV stars are convective. Hello?
Hello?
Yeah, yeah. Yeah, go ahead. Hello? Yeah. Okay, so maybe just some sort of interruption, sorry. Um, basically, we would like to actually simulate.
Dinshaw, let me interrupt. There is somebody who is asking a question. So,
okay.
So Shubham, you want to ask a question? I saw. Please raise your hand in case you want to interrupt and ask a question, so I can see it. Does anyone want to ask a question? If not, Dinshaw, please continue.
Okay, thank you. And so we would actually like to simulate problems associated with atmospheres of protoplanets, even global weather. And in all such situations, one has to model turbulence, and one actually has to do it with very high order accurate MHD systems, MHD equations in spherical geometry. So that's what this talk is focused on. It's showing how we can actually go ahead and achieve some of this. Strangely, okay. So the structure of the talk is as follows. I will talk briefly, very briefly, about geodesic meshes and the advantages they kind of give us. And then I will talk about the challenges of meshing a sphere. And I will extremely briefly touch upon algorithmic advances that have made it possible to achieve these geodesic meshes. I will also be talking next week about the details of the algorithms. So those who are interested in the details can actually attend that talk. And I will send material to Arun Mangalam on how to sign up for that. Then we will actually get into the meat of this talk, which is radiatively driven winds and massive stars. And I'll talk to you all about the physics of the simulations. Namely, it all comes down to three important parameters that regulate the formation of winds in such circumstances. And we will discuss those parameters and discuss how they play out. And then we will actually go ahead and talk about mass and momentum and angular momentum loss in these stars. Then we'll have some fun with watching movies about dynamical magnetospheres, centrifugal magnetospheres, etc. And then we'll talk about mass and angular momentum loss in these massive stars, because we know that these massive stars lose a significant amount of their mass during the course of their very brief lives. But if they lose mass, they basically end up as different supernova end states from what they started off as progenitors, and what they started off as as the masses with which they started off their lives. And so we actually want to get a handle on mass and angular momentum loss in these magnetized massive stars, and then I'll actually go ahead and talk about some conclusions. So we've already seen that meshing the sphere with spherical coordinates has a lot of difficulties, namely small time steps, loss of accuracy, and worse yet, fictitious heating of the poles and divergence buildup in the magnetic fields. And so we would actually like to get past this. And if we actually cast further, a little further on general relativistic systems, we realize that we would actually like to go all the way to the event horizon and not have our codes blow up. And so we want simulational capabilities that offer the maximum angular isotropy on a sphere. And the question of how to achieve that comes up by understanding the Platonic solids. Namely, these are solids that were actually in Euclid's geometry 2000 plus years ago. And imagine, if you like, a 20-sided figure, namely an icosahedron, one of the perfect solids that Euclid talked about. And imagine just blowing up till it matches up with the boundary of a sphere. Then you have a way of actually meshing the sphere with these triangles. And these triangles are completely bias-free. So you can imagine that the first meshing of the sphere would be a great triangle like this one, for example. And the boundaries of this great triangle are made up of arcs of great circles on the surface of the sphere. And this actually gives you a resolution from here to here of around 63 degrees. Of course, that is a very poor resolution. So what you do is you go through a further subdivision like out here, and then that gives you a resolution, an angular resolution of 31 degrees. Again, not spectacular, but you can keep repeating this process, and the end result is that you arrive at something like this after about 5 repetitions of the process, and this gives you an angular resolution of around 4 degrees. And we can actually continue this process as many times as we want. And typically in the simulations that I'll show you today, we've actually achieved an angular resolution of just 2 degrees. And that actually allows us to cover the surface of the sphere with a sequence of triangles which make for very efficient processing. And actually, because each of these triangular patches can be sent and processed on an individual node in a supercomputer, it actually opens the door to achieving excellent parallelism and adaptive mesh refinement. So there's actually many benefits that come from having such a simulational capability. And then we actually want to do three-dimensional simulation. So exactly how do we do that? The answer is very simple. You just take this two-dimensional mesh and extrude it further in the outward radial direction. So you actually go ahead and put many zones in the radial direction, and that gives you a three-dimensional mesh that completely covers a sphere in the most beautiful way possible. And then you go ahead and you're ready to do your simulations. Now, interestingly, if I block out one of the zones on this mesh, you actually realize that this would be one of the zones on this mesh. And you can actually see that the zones on this mesh actually form something that resembles a triangular prism, but not quite. And so you have something that resembles a triangular prism. It's actually, the technical name is called a frustum. And you realize that this frustum is logically equivalent to a triangular prism like the one shown out here. And so there's a, you now have
Dimsdale, can I interrupt you for a second?
Yeah, go ahead.
Yeah, you see, you're using basically great circles, right, to map this the sphere. You break up the great circles at logically, equidistant points, and then you make different triangles, right?
Yeah.
Why do you use triangles? You could do this with I suppose squares being the basic unit.
You could do that, and we've also done that. You've also done that. Yeah. So
So
there might be the benefits to using squares, there are benefits to using triangles. One of the benefits to using triangles is that they are completely isotropic. Okay. The squares are not as isotropic, but they're easier to process on a supercomputer. So there are benefits both ways. What you want to do is actually set up quadrature, and you realize that a volume, for example, out here would be smaller than a volume, for example, out here. And so there's a process called an isoparametric mapping, which actually allows us to achieve this quadrature points inside areas and volumes on a great sphere, on a great circle. And that allows us to actually go ahead and set up a mesh. Once you've set up a mesh, the gold standard in simulation is to actually go ahead and use what is called a constraint transport strategy, where the magnetic fields are collocated at the faces of the mesh and the electric fields are collocated at the edges of the mesh, as you can see out here. And we can actually go ahead and replicate the same logic on the frustum that we have on the right. So it takes a little bit of doing, but it can actually be done. And that allows us to have the best of the best numerical MHD methods on a spherical mesh. And the result is seen out here, where we see that even for up to 100,000 processors, we can achieve perfect scaling with our simulational codes. So with that said, let's now go into the science and talk about the science for the next 45 or so minutes. Did we have any questions about the previous part?
Well, I was just curious about this, the tiling, as you probably call it. the basic advantages that you're using geodesics, I suppose, in this system, you would have the longitudes, which are great circles, but then the latitudes are not great circles, and then you have to patch it up with segments which are great circles, right? From point to point.
Not really. There's no concept of latitude and longitude. Any concept of latitude and longitude will necessarily give you coordinates.
No, but the longitudes. If you just use longitudes, they're exactly great circles. So from geodesically, they're okay. But the latitudes are not great circles. So I was just saying that if you try to tile the sphere with, I mean, you obviously use the scheme to tile it. And the main motivation for this procedure is saying that is because you find the numerical computations more efficient, correct?
Yeah, that's right. Okay. So yes, that's right.
My question would be, of course, you would have built coordinate systems, and then you're using the coordinate systems. But when you're using the physical flow, right, you've got to put the physical flow also in these new coordinates, which seems to be at each point. You have the grid on it, and then you have to sort of break down the velocities and everything within this grid. Right?
Yeah, that's right. Okay, so let's go ahead and focus on the science now. What's the difference between a massive star wind and, for example, the wind around that comes from our solar wind? And the primary difference is the extent of the massive star wind. So a massive star basically has about 10 raised to minus 6 M solar per year coming out of it, whereas a star like our sun has much lower amount of mass outflow coming out of it, more like 10 raised to minus 14 M solar a year. Now, the difference between a massive star and our sun is that a O-type star would basically be emitting luminosity that is 1,000 to 10,000 times more than our sun. And as a result, these massive star winds are lifted off by just the radiation pressure that pushes on it. Whereas with our sun, you basically have to heat up the base of the corona through using some magnetospheric processes. And then you find it possible to launch the wind. Now, the important difference is this, that because this is a gigantic number compared to the mass loss rate in our solar wind, a massive star can lose more than 50% of its initial mass over its lifetime, whereas our sun loses just about 0.1%, 0.01% of its mass over its lifetime. And it's essential to understand the evolution of these massive stars within the context of the winds that kind of they send out. And these winds are very important because they actually affect the chemical evolution, the mechanical energy, the ionization structure of the interstellar medium, and also the star formation that takes place inside giant molecular clouds. So they affect, these massive winds affect a lot of things. So it's important to study these massive winds. And these massive winds are basically driven by line radiation that comes off from the surface of this massive star. And what we call these winds Doppler shifted resonant absorption of the mostly UV radiation emitted from the star. So this is basically the driver that drives the wind from such stars. So if you just think about the luminosity of a star, of a massive star, it can be so great that it can actually, you would theoretically think that it should be lifting off the entire outer envelope of the star. But that is in fact not the case, because it turns out that these massive stars emit prodigiously in the ultraviolet, and they emit prodigiously in specific ultraviolet lines. And so you have a situation where a wind sets itself up around these massive stars. And if you imagine a photon with a certain wavelength lambda 0 coming out from the base of the star, which is kind of at this radius out here, and what I'm showing you out here is the velocity structure of the wind as a function of its radius. So if you think about a massive star, if you think about a photon in a certain line profile coming out at the base of the star, namely in the atmosphere of the star, then this photon will actually not be able to connect or resonantly connect with some portions of the wind, simply because the wind is being Doppler shifted away from the emitted wavelength of the photon that is coming out. And it actually turns out that at some other radius in this wind, maybe at this radius out here, there's some line available which again gets Doppler shifted back again so that it can absorb, resonantly absorb the photon that is coming out from the star. So each photon that is coming out from the star essentially gets absorbed in a narrow range of radii, like the one out here. And once it gets absorbed, it kind of gets scattered also. So it can kind of go outwards or it can go inwards. And that is actually what happens to the photons. But in getting absorbed, it actually provides a push or an acceleration to the stellar wind and therefore drives the wind outwards. So once we have this realization, we realize that the Doppler shifting, namely the acceleration of the wind, will play a big role in the force that you get. So this is the gravitational acceleration through line radiation. And you realize that it actually depends on the acceleration as a function of radius inside the wind structure itself. And that's an important idea that we have to factor into our thinking. Now, these winds are also susceptible to something called a line deshadowing instability. But if people in this audience are not experts on line deshadowing instability, I will just say that for the approximations that we have used in our simulations, we have kind of totally ignored the line deshadowing instability. So let's just move on. So with this, we want to simulate magnetic massive stars. And it actually turns out that around 7 to 10% of the massive stars that we have in our galaxy, that we observe in our galaxy, have very strong magnetic fields. And the interesting connection out here is that the fraction of neutron stars that turn out to be magnetars is also about 10%. So it actually tells you that there might be a connection between strongly magnetized OB stars and the eventual neutron stars and magnetars that result from such a situation. Now, one very obvious question is that how did these massive stars acquire these magnetic fields? That is a little bit of a gray area because in some sense, people have conjectured that you could have some sort of dynamo process. However, the outer structures of these massive stars are in fact radiatively stable. They're not convective. And as a result, you have to kind of fine-tune dynamo processes that might perhaps act in thin surfaces around the atmosphere of the massive star and probably build up a magnetic field. You might also think about magnetic fields being generated deep inside the massive star and popping outside, or you might actually think about relic magnetic fields from the initial phase of stellar collapse that took place. So with this, we now have to delve into the physics of these winds and what happens when you have a situation where you have a massive star. Let me see if I can move this thing out here. Okay, this is excellent. And so imagine, if you like, that we have a massive star shown in the blue out here. So that's this guy out here. And this massive star has these magnetic fields, as you can see. And so if a wind should come out here and out here, then if the magnetic field is strong enough, the magnetic field will actually channelize the wind so that it actually goes ahead and comes together in the magnetic equator of the star. Of course, if the magnetic field is not strong enough, then the wind will, of course, blow out the magnetic field and open up the magnetic field lines. And then, of course, the show is over. So the question is, what is the condition under which we could actually have massive stellar winds? I'll erase this thing. And what are the conditions under which the magnetic field of the star could be so strong as to actually confine the wind and turn it around. And the condition is that the magnetic pressure or the magnetic tension should in fact be greater than the ram pressure in the wind. And of course, that lends itself to a scaling argument where we can actually go ahead and make this magnetic wind confinement parameter, which is nothing but the ratio of the magnetic pressure to the ram pressure. And we can actually then go ahead and do a few steps, multiply through the numerator and denominator with the radius of the star, and actually obtain this parameter, which is more close to what can be observed. And that actually gives us a magnetic wind confinement parameter. And we realize that if the magnetic wind confinement parameter is greater than unity, then you actually have the possibility of the magnetic field around the star being so strong that it actually channelizes and moves around the flow of the wind that is coming out of the star. Now, interestingly, you have a situation. Let me see if I can move this guy around also. Probably not. Okay, so interestingly, we have a situation, therefore, where up to this boundary where the magnetic field lines are closed, you have the possibility of the wind being completely swept along by the star, by the magnetic fields around the star. And these magnetic fields around the star can actually provide magnetic torques, which make sure that the wind actually rigidly co-rotates with the magnetosphere out to this radius. And so you actually go ahead and say, how would we actually calculate this radius? And the answer is very simple. Namely, we actually realize that the magnetic field is a dipolar magnetic field, so it falls off as 1 over r cubed. So there's actually going to be some point at which the magnetic field becomes too dilute, and we call this boundary where the magnetic field becomes too dilute as the Alfvén radius. And we realize that as Eta Star increases, our Alfvén radius, Ra, also increases. And that's the realization that we have to keep in mind. And also keep in mind that up to the Alfvén radius, the wind material is magnetically locked by magnetic torsional forces to the rotation of the star. So now then there's these stars, many of these stars also rotate at a very high speed. And so we actually go ahead and ask, what is the critical rotation rate at which the star would break up? And that would actually be obtained if we equated the centripetal acceleration to the gravitational acceleration, and that gives us a critical rotation which should not be exceeded. Now, any star will rotate at a fraction of this critical rotation ratio, and therefore we can actually develop another parameter, namely the critical rotation ratio, which actually tells us that up to a certain point, up to a certain radius, which we call the Kepler radius, or beyond a certain radius, which we call the Kepler radius, the rotational forces, namely the centrifugal forces, will actually win. And so we realize that as this rotational ratio becomes larger, we have Kepler radius becoming smaller, basically because of the scaling effect. Now, the third parameter which regulates the wind is actually the angle made between the rotation axis of the star and the dipole axis of the star's magnetic field. And this is actually what introduces a significant amount of three-dimensionality into the problem. And we want to actually understand the problem fully three-dimensionally. So the study of massive stellar winds is a study of three parameters, or three regulating parameters. One is the wind confinement parameter, which determines the Alfvén radius, and the flow basically remains in the clutches of the magnetic field out to the Alfvén radius. After the beyond the Alfvén radius, the magnetic field lines open up and the flow can actually flow outwards. But till the Alfvén radius is reached, the wind material has to co-rotate with the magnetosphere. Then it also depends on the rotation ratio, and we understand that as the star rotates faster and faster, the Kepler radius actually moves inwards. okay? Namely, past the Kepler radius, the rotational forces become dominant. And it also depends on this angle zeta, which is actually the angle between the rotational axis of the star and the magnetic dipole axis of the star. So with that, we actually want to simulate a system like an O4 supergiant, which is Zeta Pup in this case. So we're using a template star as a way of kind of giving us something concrete to kind of sink our teeth into. So with that, we actually come up with two scenarios or two parameter regimes. Notice that this is all pertaining to the aligned rotator case. And in the aligned rotator case, we know that the magnetic torques are such that the wind material will be rotationally locked to the magnetosphere out to the Alfvén radius. Okay? Outside the Alfvén radius, the field lines open up. Now, if the star is a slow rotator, namely if omega is really small, then the Keplerian radius is really large, and the Alfvén radius is smaller than the Keplerian radius. And in such circumstances, the magnetic field of the closed magnetospheric field lines will actually dynamically channel the flow that takes place in the wind. Now, what if you have a situation where omega becomes large? In that case, you have a situation where the Keplerian radius moves inwards as omega becomes larger and larger. And at some stage, the Keplerian radius can actually become smaller than the Alfvén radius. In such a circumstance, we have a very interesting situation, because for all radii outside the Kepler radius, the wind is actually centrifugally flung by the rotation, and more importantly, the magnetic field holds it in place. Namely, the magnetic field makes it co-rotate. And in that situation, in the region between the Kepler radius and the Alfvén radius, you have a situation where that region is essentially filled up by flow that is flung into that region, and you have a centrifugal magnetosphere. In other words, this magnetosphere will basically build up matter between the Kepler radius and the Alfvén radius, and episodically, it will actually go ahead and release that material. Now, this is only for the case of an aligned rotator. So we have to ask the question, if we have a non-aligned rotator, then how does this scenario change? And that's actually a fertile area for using computational astrophysics, because computational astrophysics is the only thing that we have, is the only tool that we have for exploring these geometrically complicated circumstances. So what we've done is done a whole range of simulations.
Excuse me, can I ask one question now?
Go ahead.
Please,
yeah.
go ahead.
Yeah. So in your this previous figure in the magnetic field diagram, so do you only consider these fields are like poloidal field, not any toroidal components?
Well, they will acquire a toroidal component because, in a sense, they're actually trying to give some of their angular momentum to the matter. So in doing so, they will actually go ahead and get and be turned into spiral type structures if you could look from the top out here. Right?
So due to flux frozen condition or something like that, it is rotating.
So all of those conditions are built into the code, and then the code grips and does whatever it needs to do.
Okay. And another question is, how do you differentiate between in this scenario a jet and wind? So it is a jet outflow or like a wind outflow? How do you differentiate?
There are no mechanisms for jet formation as such in this situation. So there are no known jets coming out of magnetic massive stars. So it's basically all wind.
Okay. Thank you.
Sure. So
I just want to point out that, in analogy with Weber and Davis, the spiraling or the field lines happens quite naturally after the Alfvén radius, right? So up to the Alfvén radius just follows the field lines, and then it gets twisted up as it gets out. So in that figure,
you'll see a little bit of Weber-Davis.
Sorry?
Saran,
Yeah.
you'll see a little bit of Weber-Davis coming along as we move into angular momentum loss and things like that. So
just one
let's go
comment
ahead
that
and
you
start.
made in the beginning, Dinshaw. It's about you discuss M over M dot, but I guess the basis of of this problem is also J over J dot, right?
Yes,
And
that's right.
And that's very astrophysically important because
yeah. So
you know
we will
it's relevant to your time scales. How
yes, that's right.
you know what is your
yes.
time steps, right?
That's fantastic question because it anticipates the rest of this talk essentially. So let's go ahead and see what we have simulated. So we actually go ahead and simulate as a point of reference a non-rotating, non-magnetized wind around a star. But then we also go ahead and assign to it a certain amount of rotation. And that's important because in a sense, we want to understand the effects of rotation, the effects of magnetic field, and then the effects of magnetic field and rotation. So in the third simulation, we actually go ahead and have magnetic field, but zero rotation. And in each circumstance, please note that I can actually go ahead and evaluate the Kepler radius as well as the Alfvén radius. And now that we're on board with this, we can actually use our criterion. Ra less than Rk means we have dynamical magnetosphere. Ra greater than Rk means we have centrifugal magnetosphere. So these three simulations actually provide us useful references. And then we go ahead and make three more simulations where we spin up the star, and we also go ahead and introduce a certain amount of tilt to the angle between the rotational axis and the magnetic dipole axis. And then we actually go ahead and have an even stronger magnetic field out here with no rotation. And then we actually go ahead and spin up that situation, which is what is done out here, again, making a bigger and bigger angle between the rotation axis and the dipole axis. Now notice that because I have tabulated Rk and Ra, I can make a theoretical estimate of which one should be a dynamical magnetosphere and which ones should be centrifugal magnetospheres. And we'll see how well our theoretical estimates hold up in light of actual practical simulations. So the first thing that we can actually do is let these simulations rip and let them reach steady state. So if you let them rip for time scales of several days or weeks, you can actually go ahead and have a steady state. And this is actually anticipating or giving an answer to part of what Arun asked, because it's basically telling you that you have the mass outflow rate as a function of time. And here on the left top panel, we've done it for no rotation and no tilt. In other words, the eta is equal to 10 is a smaller magnetic field. The eta is equal to 50 case represents a larger magnetic field. And you see something very, very interesting, namely the stable eventual mass loss that takes place in a magnetized star with a smaller magnetic field is higher than the stable eventual mass loss that takes place in a magnetized star with a higher magnetic field. And that's interesting because it basically tells you exactly what you intuitively expected, namely that the magnetic field confines the outflow and basically prevents the outflow from taking place over certain parts of the surface of the star, thereby giving you a lower overall outflow rate. Now let's go ahead and consider the situation where you introduce rotation and two different intensities of magnetic field. And again, you see the same trend, namely, if you have smaller magnetic field, you have higher amount of mass loss. If you have bigger magnetic field, you have lower amount of mass loss. And now we can continue this. And so we can say, what is the role of tilt in going ahead and giving us the mass loss? And if I tilt it even further, namely make a bigger angle between the rotation axis and the dipole axis, this is the rotation axis, this is the dipole axis, and therefore I can actually go ahead and have, I can estimate the role of magnetic fields in regulating outflow in these massive stars. And we realize that higher magnetic fields means you have lower mass flow. So this actually gives us our first answer to Arun's question. And let's go ahead and delve a little deeper into this. So here I've shown you three different plots: density as a function of radius, radial velocity as a function of radius, and overall mass outflow as a function of radius. And let's go ahead and first focus on the black and red lines in this plot out here. So the black line shows a reference calculation with no magnetic field and no rotation. And the red line shows the situation where we have no magnetic field, but we have cranked up the rotation. And you can see that introducing rotation actually will increase the mass flux. And that's interesting and nice to know. So it basically conforms with our expectations. Okay, now let's go ahead and compare our reference calculation, which is this guy, again, the black line, to a situation where we introduce a magnetic field, namely this orange curve that you have out here. And you can see that introducing a magnetic field has caused a dramatic drop in the amount of mass flux coming from the star. So increasing magnetic field will basically decrease the mass flux. And that's an interesting thing to understand. And now let's go ahead and say that we take the same magnetized but non-rotating star and we spin it up. And we spin it up so that the axes are aligned between the rotational axis and the dipole axis. And then we actually see that introducing a certain amount of rotation actually gives us a larger mass loss rate, exactly as expected. So this is a very good thing. So increasing rotation, even for a magnetized star, will give us increasing mass flux. And these last two simulations out here basically show us what happens when we increase the tilt angle. And as we increase the tilt angle, we see that the mass flux decreases. And that too makes sense, because if your magnetic axis is tilted relative to the rotational axis, then you have a smaller moment arm from your magnetic dipole, and therefore you're less likely to fling material outwards. And so your mass loss is reduced. And so this actually tells us that increasing tilt will create a situation where we have decreasing mass flux. Because of this.
Just one interesting point. Your result here, the Weber-Davis actually is an equatorial result. I mean, it's the calculation is completely equatorial. So yes, there, if you increase the magnetic field strength, what you're trying to do is keep, I suppose in that situation, you would get, for the same constant spin, you increase the field, the RA goes out and you get a higher mass flux. But here you have a sort of a poloidal structure. And if you increase the field strength here, you're actually blocking the wind or
yes, that's right. And so the difference between Weber-Davis, yes. So that's a fundamental difference, and the Weber-Davis situation is completely unrealizable in real life, because they either use a split monopole or a pure monopole, whereas here we're actually allowing for closed field lines that take place in a real dipole. So this is a somewhat more realistic situation. So you're absolutely right.
And when you calculate your mass flux, I suppose you're putting a sphere somewhere and calculating.
Yes, you put a sphere at the outer boundary and you can calculate the mass flux. But as you see out here, we have the mass flux evaluated at all possible radii. So that makes sense. And there's also evidence for fast wind at the magnetic poles and slow wind at the magnetic equator.
So, and in the case when you have a tilt, do you have a mass flux as a function of the angle or
yes, we do. And I will show you some visuals to kind of bolster that point in a little bit. But let's go ahead and now have some fun, because every computational talk should have some nice movies in it. And so let's go ahead and have movies now. So we have a situation here where we have a magnetized star, no rotation, W is equal to 0, and no tilt, namely zeta is equal to 0. And let's go ahead and see this situation. In this circumstance, the Alfvén radius is 2.1 times the stellar radius, and the Kepler radius is, of course, infinity. So we have a situation where the Alfvén radius is smaller than the Kepler radius. Therefore, we expect to see a dynamical magnetosphere. Let's see what a dynamical magnetosphere actually looks like. So you see first that the wind is being squeezed out the equator, but very shortly, the wind is restricted from flowing out, and as a result, the wind forms these clumps, as you can see, and these clumps start falling down back on the surface of the star. You're seeing the third clump falling down on the surface of the star, and these clumps actually go towards filling out the star's magnetosphere, as you can see out here. So we can actually go ahead, run the simulation again, and you can see the clump formation because the wind is, there's an initial transient phase, but then you can see the clump formation with the magnetic field reining in the outflow. As you can see out here, there's another set of clumps that are falling back onto the star and filling out its magnetosphere. Now you see the same process happening over again. And that's kind of very interesting because it actually goes ahead and makes everything vivid and visual. So let's go ahead and now move on to our next transparency. And this actually just shows it by way of stills. But now let's go ahead and consider a situation where you have, again, a same magnetic field, but now you introduce some rotation. And in this case, your Alfvén radius is 2.1 and your Kepler radius is 1.59. And of course, all of these are scaled relative to the stellar radius, which is unity. And therefore, you actually see that now you have a competition between the Alfvén radius and the Kepler radius. Theoretically, the RA is larger than RK, so you expect to see a centrifugal magnetosphere. But let's see if the dynamics of the situation is actually consistent with a centrifugal magnetosphere, or maybe our scaling estimates are not exactly perfect, and therefore we achieve a dynamical magnetosphere. So let's see what happens out here. And you see that, again, you're filling up the magnetosphere, and now you're going to start seeing the clump formation just in a few seconds, maybe. Okay, so now you're seeing the clump formation, and you're seeing the clumps kind of going ahead and landing back onto the star. And you're seeing the second clump also forming and trying to land back onto the star. And so you're seeing the star's magnetosphere fill up within a dynamical fashion, which basically means that even though in principle this should have been a centrifugal magnetosphere, the difference between 2.1 and 1.59 is small enough that you're actually going ahead and producing a dynamical magnetosphere. So now let's go ahead and see what happens if we have a much larger magnetic field, so that our Alfvén radius is 2.9, whereas our Kepler radius is 1.59. And we have a very strong rotation. In that case, we expect to see a centrifugal magnetosphere where there's mass sloshing just between RK and RA. And let's go ahead and roll the movie. And you can see episodically that these field lines will keep moving out and in, indicating that the seepage of matter that is collected between the Kepler radius and the Alfvén radius. But again, you're seeing no clump formation, which basically is a dead ringer suggestion that we've achieved a centrifugal magnetosphere, not dynamical magnetosphere. So actually the theory is borne out. It's just that the theory is not exactly perfect because the theory was just based on a scaling argument. So
do you have a view from the poles? I mean, that would be interesting.
But not right now, Arun. Not right now. So
the other thing is that I suppose it's it's an O star and the wind is radiatively launched, right?
Yes.
I was just curious to know where your sonic points are and magnetosonic points. And,
yeah, this is all rolled into the ball of the simulation. So
yeah, I understand that. Yeah, thanks.
Okay. So now let's go ahead and consider a situation where we have the same situation, namely Eta Star of 10, W of 0.5. This situation had turned into a dynamical magnetosphere before, even though it was theoretically slated to become a centrifugal magnetosphere. And let's go ahead and see what happens if we introduce a tilt of 45 degrees. In other words, the rotation axis is still along here, but the dipole axis is making an angle of 45 degrees. And let's now go ahead and see what sort of magnetosphere we get. And we immediately see that we indeed have clump formation and the signatures of a dynamical magnetosphere. Interestingly enough, now the matter is not coming out from both the foot points of this magnetic field, but only from one of the foot points. And that too is comprehensible because this foot point is at a larger radius relative to the rotational axis, and therefore feels a bigger centrifugal force, and that is what allows us to understand this situation. Now let's view another situation where we have an even larger magnetic field, namely an Eta Star of 50 with a high rotation rate. And in that case, we had seen before that the Alfvén radius is much larger than the Keplerian radius, and so we expect to see a centrifugal magnetosphere. However, because of this cosine theta factor, we realize that Ra times cosine theta is actually quite comparable to Rk. And so let's look at the kind of situation we have. So what used to be a centrifugal magnetosphere now seems to be turning into a dynamical magnetosphere, as you will see very soon. And again, you see the clump formation and the fallback of these clumps onto the star. These clumps are important because here we're showing you just an isothermal simulation, but when these clumps form, they actually go ahead and produce X-ray emitting shocks with the rest of the wind structure. And that is actually something that observers can indeed observe and identify. So you see second or third generations of clump formation now taking place. The interesting thing is that now the magnetosphere, because of the tilt, is not filled in the classical sense of two cups or two dongles that you see around the star, but it is nevertheless being filled in an interesting geometrically complicated structure.
Dinshaw, I'm just trying to understand your color density here. It's reflecting density, but it's a column density. What is this?
It's just a slice, and it's just showing.
Oh, it's a slice okay, right. Okay, so it's a plane passing through the pole.
That's right. That's right. And now let's go ahead and crank it up really hard. So strong magnetic field, strong rotation, and very large tilt, and see what happens. And in this case also, with the cosine zeta factor, we see that Ra cosine zeta is actually smaller than Rk. And so, again, we see a dynamical magnetosphere developing out here. Again, you see clump formation and clumps wanting to kind of go ahead and land onto the surface of the star, which is an interesting phenomenon. Again, the magnetosphere is not classically filled in the way we think about it, but it is nevertheless getting filled in. So with that, I'd actually like to show you planes, namely XY plane, XZ plane, YZ plane. Remember, the rotation axis is the Z axis. And that actually shows you that these filaments or clumps that are forming and structures that are forming are actually very complicated three-dimensional structures that are forming around the star. And there's just different views of the velocity and the magnetic field that I can show you. Of course, that just shows that there's a very complicated geometry developing in the wind. But now let's go ahead and answer the actual detailed question that Arun was interested in, namely, can we actually quantify the mass loss and the angular momentum loss? Because that is the thing that is actually, the movies are fine. They kind of give you fun, they give you perspective, but then the numbers is what carries the day. So this is actually showing an aligned rotator with a magnetic field and very strong rotation. And you actually see that the angular momentum is coming out initially along the magnetic field line. So it's the magnetic torques that are initially carrying the majority of the angular momentum. And this is actually just showing you a zoomed in version of this guy. And as you go outwards, you realize that then the matter is carrying more and more of the angular momentum, while the magnetic field, because it kind of dies out as 1 over r cubed, is carrying less and less of the angular momentum. Interestingly, let's look at this panel out here, this middle panel, which shows a situation where you have the same configuration, but with a tilt of 45 degrees. And you can actually see that the angular momentum is coming out along here and along here. And you can actually see in the zoomed in image that a large amount of angular momentum is again coming out along open field lines. This is actually part of what you wouldn't see in a Weber-Davis solution, because the Weber-Davis is just restricted to the midplane. And now we can actually go ahead and take this further to a 75-degree tilt, and we can again see the same trends, namely it's the open field lines that carry a majority of the angular momentum close in the star, but moving outwards, it's the mass that again carries the angular momentum. So with this, we can actually go ahead
if I were to ask the question, sorry to interrupt, it's a very interesting diagram. If I were to ask the question about angular momentum loss, there is the torque, there's a magnetic torque. I mean, there's a loss to the magnetic field by the magnetic torque. And then there is, in addition to this electromagnetic torque, you have the gas. But the gas, as you said, comes back, right? In certain places, it falls back. So when you're drawing a sphere at some point and asking the question, what is the total loss of, I mean, what is the spin down of the star, right?
Yeah.
There would be some part that is going into the torque and the electromagnetic loss of angular momentum.
So what you expect to see,
inertia,
what we expect to see is very episodic angular momentum loss. And I'm actually going to come to that in a few transparencies. So I will actually address exactly that issue that you're asking. So you can actually see that this is a representation of the mass flux at the outer boundary of the sphere. So you can see that, first of all, you're getting mass outflow along the majority of the dense outflow is along the dense wind that takes place along the magnetic equatorial magnetic equator of the situation. And you can actually see that clump formation ensures that the episodic ejections of high masses taking place out here. Now, if you go ahead and plot out the angular momentum, you can again see the same trend of episodic clump formation. Of course, at these large radii where you're actually seeing the outer boundary color-coded with angular momentum loss, you're basically seeing episodic ejection of angular momentum. But let me go ahead and now quantify this for you exactly as I told Arun I would. So this black line shows you the averaged run of total angular momentum as a function of radius. The red line out here shows you the run of magnetic angular momentum flux as a function of radius. And the blue line shows you the run of gas angular momentum flux as a function of radius. And so it's interesting that as the angular momentum drops off in the magnetic field, namely as the magnetic fields become diluted as you go outwards and they carry increasingly less angular momentum, that's when the mass, that's when the gas gets spun up and it's actually carrying more of the angular momentum. And that's actually what you're seeing out here. Interestingly, if the magnetic field becomes very strong, as is the case in these lower three panels, then you can actually see a situation where the majority of the angular momentum is indeed carried all the way through by the magnetic field and not necessarily the gas. So it's an interesting scenario that you actually understand. Now you will very well ask, what are these thin lines that are around these fat, thick lines? Namely, this thick black line has thin lines around it. Namely, so likewise, this thick red line has thin red lines around it. Likewise, this thick blue line has thin blue lines around it. These are actually runs of angular momentum at different episodes. So at different episodes, you have different amounts of angular momentum being cast out from the star. And the solid lines that you see in this figure are just time averages of the eventual, on average, steady state angular momentum loss that you expect to see in the star. So does that answer Arun's question of saying that maybe
this is a wonderful plot, and it's quite interesting. I would just be, trying to understand this from a point of view of the lifetime of the star, right? There is a m over m dot, which is, as you said, you've given us some idea of what it is for the sun or for the
So that's your next transparency. So basically, for all of the simulations that we run, we can actually evaluate an m dot and a j dot, and we can actually compare that j dot relative to the Weber-Davis solution. So this is not a white dwarf, but it is the Weber-Davis solution. And we can actually go ahead and tabulate from that the mass, the time scale over which the star will lose a significant amount of its mass, as well as the time scale over which the star will significantly spin down. And so let's first focus on this column out here. And you see that the unmagnetized cases, which are these two cases, have a time scale for mass loss. I'm sorry, the unmagnetized cases are these two cases out here. These two cases show that a majority of the mass can actually be lost in about 16 million years, which is reasonable and comparable to the lifetime for a 25 M solar star, which would be about 10 million years, which basically means that if the star is not magnetized, it has the potential to lose a significant amount of its mass over its lifetime. And that's exactly what we know and expect for massive stars. So 25 solar mass star, which started its life as a 25 solar mass star, will not be a 25 solar mass star when it goes supernova. It will probably be a 12 or 15 solar mass star because it has lost a lot of its mass to winds. Now let's look at the situation out here. So you see out here that once you have strong magnetic fields out here, which is these four panels, then you actually have a much larger time scale for mass loss. In other words, the star becomes inefficient in losing its mass, or in other words, the magnetic field is serving to kind of hold in the mass of the star and not letting it move out as quickly as you would like. If you have stronger magnetic fields, as is the case out here, then you have even more mass being retained, namely the time scale over which mass is lost becomes even larger, and therefore you understand that magnetic fields can be very good for forming very massive supernovae in the end, because in some sense they give the star a channel for retaining much of its mass. Now let's look at this, which is the time scale for spin down, and you actually see that the time scale for spin down, especially for the magnetized cases, is very, very small, less than 1 million years. And so this is actually very interesting because it actually tells you that a magnetized, rapidly rotating massive star might actually represent a very short-lived phase, after which the star, by virtue of its magnetic field, manages to shed itself off most of its angular momentum. And this is actually reasonable because we do not see too many highly spinning, fast spinning magnetized stars. Many of the magnetized stars that we see are actually slow rotators. And that is so even if they've been spun up by processes such as common envelope evolution. So this actually brings the story together by making it quantitative. And with that, if there are no further questions, I would like to move on to my conclusions, which is to say that we've achieved an ability to simulate spherical systems, which is very interesting and could apply to a lot of astrophysics, space physics, and geophysics applications. And we've studied in detail the massive magnetized star winds. We've found quasi-static solutions, namely not static, but quasi-static. We've actually studied the tilted dipole case, namely the case where the rotation axis is so, and the magnetic dipole axis can make all angles relative to the rotation axis. And we've studied the physics of mass and angular momentum ejection in this situation. And we've shown that increasing magnetic field decreases the mass outflow, whereas increasing rotation increases the mass outflow. And the tilt also suppresses the mass outflow. And we've actually been able to quantify the mass loss times and the spin loss times for these stars. And in the future, when we have more detailed simulations, we'll probably be able to simulate the H-alpha and X-ray and radio signatures from these stars. So with that, I will essentially thank you very much for your attention. And if you would permit me one more minute, I would actually like to go ahead and make this little announcement, which is to say that next week, next Thursday, I'll be talking about the same topic or similar topic, namely GeoMesh MHD, but this time talking about algorithmic paradigms that make it possible for having such simulations. And this might actually be perhaps interesting to younger students who are more interested in computation. So if you're a younger person who's more interested in computation, please go ahead and come to this talk. And if you're interested even more in computation, we have a whole sequence of talks lined up for you. So if you want information about those talks, please approach Professor Mangalam and he'll give you more information. But
in fact, what I'll do is I'll just, and you can do that too, Dinshaw, just put this in the chat box, the link, or
okay, why don't I just email it to you? I email it to you. And
okay,
you
I'll email it to you and I'll just circulate it. Yeah,
somewhere, yeah, that would be good.
So Dinshaw welcomes questions. So anybody wants to ask, please go ahead.
Can I ask a question?
Sure.
Yeah, please.
Hi. In your movies, where you show the density slices, in most of those movies, I see this field lines little far away getting kind of squeezed in by the flowing gas, but whereas the clumps which fall back do not seem to perturb the magnetic field lines. Is that really happening that way?
No, the clumps also do perturb the magnetic field lines, but as they kind of flow inwards, the magnetic field is very strong. So it basically, the magnetic field gives the mass clump its marching orders. It says, go this way, you cannot go any other way. And so that's what the clump does.
All right, okay. I have one more question. In your early part of your talk, you kind of mentioned about the thin convective layer at the massive star. I'm not sure if you use that argument to explain the origin of magnetic field, or aren't there, the massive stars have the convective cores, don't they cover the magnetic field? Is that
exactly. So that's the idea that I've actually favored, but it hasn't been favored in the literature, which is why I kept quiet about it. But our Earth also has a convective core. Nothing in the Earth's crust or mantle is moving around. And we nevertheless see a magnetic field at the surface of the Earth because it's the magnetic field in the core that is actually popping out. And it's possible that because these massive stars have convective cores, they have a dynamo operating inside their convective cores. And what we're seeing outside of the surface is those events where the magnetic field has actually succeeded in popping out from the surface of to the surface of the star. So it's possible. It's a very good hypothesis.
But for the dynamo to work, you of course need the convection or some kind of a poloidal motion, but differential rotation is also required, which I don't know how rigidly rotating. Sometimes it's a question of how rigidly rotating the core is, right?
So the interior of a massive.
If you have rigid rotation, then you're not going to get any dynamo process.
if you have rigid rotation, then you will not get a classical dynamo. You could still get a fast dynamo.
Probably.
So so then it's all up for grabs.
All right. So what's the current scenario for massive stars, the original magnetic field? Is it?
That's another talk altogether. That's not my talk.
Okay. All right. Okay. Thank you.
Sure.
Any other question? Dinshaw, I have a couple of remarks, maybe a question. You see, this is very interesting in the sense you predict a J over J dot and an M over M dot, but it's actually a snapshot of the star during its evolution, right? I mean, you're talking about timescales which are millions of years. So I think your simulation runs for how many years? I don't know how.
The simulations basically run for days to weeks.
Days? No. In the timescale of the star, how long?
Yeah, the simulations run for days to weeks because they're quasi-static phenomena that keep repeating. So there's no point in kind of running them after they'll just repeat the same.
Right. So you get numbers which are sort of fiducial in terms of, you know, the time scale of spin down and so for various initial conditions, and then there's another parameter which you could play around with. I suppose it's the when you're using Eta, it's sort of the balance between the rho v squared and the magnetic pressure, right? And then you have the other one, which is the rotational speed and gravity, right? So now you could also have a case, which you mentioned in one of your slides, where you increase both the magnetic field and the rotation. So both are large, which could happen in some situations. And of course, you would spin down the star due to, it would be an interesting balance, I think. Because there, the magnetic field would spin down the star, and then the W.
You're right, Arun. You're right, but there's one more complication that comes in, which is to say that all our theories about radiative driving and how it all works and all that, they break down when you have extremely high rotation rates and very strong magnetic fields. So you know, because we need the support of CAK wind theory, and the theory is not available in those limits that you mentioned, you know, we could in principle run a simulation, but then, you know, what is that simulation telling you? That's the question.
Okay. Just one last comment. That if you look at a survey of stars with, I don't know if there are actual realistic, I mean, stellar surveys of O stars, where you look at
there are surveys that are taking place. You know, there's a huge amount of Hubble time that has been allotted to both groups of American scientists and groups of European scientists to do such surveys.
Yes. So if you look at it in some kind of a diagram, which I would call the BJ diagram, or you know, the spin, I mean, M dot J dot diagram, like, you know, you have certain diagrams for pulsars, right? So I suppose you know, some sort of analogous diagrams where you can look at the population of these, you know, this J dot M dots from the surveys, and then compare it, and probably you can sort of try and match it, because there, in your quasi-static final results, there are ratios, interesting ratios that seems to be emerging, which is a consequence of Eta and W. So maybe there is something that would be providing clues on the evolution, right?
Yeah, there are people in our group who are observers, and they would like to make this complete butterfly collection and do exactly what you're saying. So we will just wait and let them do it.
Okay. Great. It was a very nice talk. Good, you know, pictures and simulations, I suppose.
Thank you most kindly. Thank you
This
most
is,
kindly.
could you just tell us a little bit about the kind of, where you're running are these supercomputer simulations, or what kind of clusters you're using?
So these can be run on any typical modern cluster with maybe 1,000 or 2,000 cores. So it's kind of even a university class cluster can kind of do the job. And especially in the Indian context, I mean, the government of India is buying these supercomputers for individual institutes with 1,000, 2,000 cores. And there we also have a significant investment in GPU computing. So even with maybe 16 or 32 GPUs in a cluster, you can actually run these simulations quite comfortably.
And the specific advantage is you've gained because of the way you're doing the geodesic grids.
That's right.
And so that gives you, buys you
that frees you up from the four curses of using an R theta phi type mesh, namely small time steps, inaccuracy at the poles, fictitious heating of the gas that moves over the poles, and the divergence-free aspect of the magnetic field.
Great. Well, are there any questions? I'll forward certainly the talks that Dinshaw is going to give at IIT Delhi, and there will be a link which I'll circulate. And if there are no other questions, we'll thank Dinshaw.
Thank you very much, folks. Thanks a lot.
Thank you.
See you all.